Apparently she's 17.
Okay, so let's talk about big ideas that are going to be on the final. Okay, so what I might do is like strategically combine things into like different things. So I might say, okay, here you have like a syringe, and it's a certain distance above the ground, and I might say, all right, I want this thing to land a certain distance away, say 4 meters, and I tell you that it's 2 meters above the ground, and this opening is 3 millimeters, and then I'm going to ask you how fast do I have to push this plunger to make that water land 4 meters away. So,
Using the equation.
and the radius
don't like this.
of that diameter is
Radius.
2 centimeters.
We have to do this and projectile motion.
In one.
Yes.
Well,
I don't
actually,
like
once you
this.
get the velocity as it leaves, right, it'll fall like any normal thing, right?
Well, you gotta find the velocity that it
remember,
takes for it to travel a distance. of
Water
4
is
meters.
gravity dampening, so it's not gonna fall. at the same
Don't.
rate.
Oh, you're right. I forgot about that one.
That's
The-
only when it's in a glass container. This is not water, this is not
This
gravity.
is normal water.
Normal gravity, actually.
Oh, but you gotta find the. Well, once you find the height, then you have the time. Then you find then you need then you know the velocity that it has to leave the tube at, and then you can solve for the velocity which you push the plunger.
Yeah, so basically, at the end of the day, you want to use area 1, velocity 1 equals area 2, velocity 2, right?
Sure.
True?
True. Yep.
So
That's the first one.
Very true.
so first we need to find the time it takes to fall.
Yep,
So
because it has room to fall.
it does.
It does
Therefore, it
indeed have
must.
that.
Use that equation. So-
No,
No, that equation does not include time.
Dang. Use not that equation.
how about x equals 1/2 at squared plus,
V naught t.
Yep. Not that equation.
not that equation,
V naught t goes to 0 because it's vertical.
it's, well, it's horizontal, but
Well, yeah, but I mean, you know what I mean. Like it's moving like
It's in a
this, so
direction.
but it's not moving like this. So like,
it has no vertical.
yeah, because it's vertical.
That's not what you meant.
That's not what you.
What?
That is what I meant.
Okay.
That's what I
Okay.
meant. That's not what I
A's-
said.
A's-
So,
There is
since I just
vertical,
made this
but-
up,
No.
Yeah.
so 2x
too big
over
to solve.
a and the square root of that times, so what do you get for your
Solve
time?
the x.
0.639.
0.639 seconds.
It's not starting moving.
So,
It's not
will that
moving.
be
Yeah, 'cause it's
impacted
vertical.
by the
makes
speed
sense.
of that
Yeah, but
plunger
it's still moving in the vertical direction.
Yes.
as it moves?
No.
No.
Absolutely not. Why?
Change the height.
Well, it's the only thing that determines how long that thing is in the air,
The height.
Height.
the height. That's
Oh.
it. Okay? Nothing else.
Unless it's
As
going
long
fast
as
enough
it's
to leave orbit.
horizontal and not,
Going fast
vertical.
enough to leave orbit.
huh?
As long as it's horizontal and not going
Yeah, we're
fast enough to
assuming
leave
that we're
orbit.
not going fast enough to put the water into orbit.
Okay, so meters per second, so 4 divided by 0.63.
So then you kind of go, oh, range equals Vx time, which is nothing but a fancy way of saying distance equals velocity times time, because there is no acceleration, which is just basically this equation without the acceleration part, which basically says, oh, distance equals velocity times time. Okay? That's all that is. So I wanted to go 4 meters, so Gap Sean, take 4 meters and divide that by that time of 0.639 seconds.
You get 6.26.
What'd you get?
6.26.
6.26 meters per second. Okay, cool. Now we can come down here and go area 1, velocity 1 equals area 2, velocity 2. So now we've got the second velocity, which is going to be 6.26 meters per second. Now, how are you going to calculate the cross-sectional area of the end of that syringe,
Pi r squared.
pi r squared. Now let's just write that as pi r squared. That's gonna be pi, and then you're gonna have 3 millimeter.
Tasty.
So then you got a 3 millimeter radius, which is gonna be a,
0.000.
or excuse me, a 3 millimeter diameter.
Oh, so which is the 1.5?
The diameter is 3 millimeter. So, yeah, Sean, take 3 divided by 1,000 divided by 2.
0.0015.
0.0015 squared. Now, over here, that's gonna be pi, and that is a 2 centimeter
Stupid dimensional.
diameter plunger. So that's gonna be 0.01.
Yeah, and then you do all the cancel, and then you have.
Now, here's the beauty of this, times V1. So actually, to save you a little bit of hassle, what's gonna happen to pi? Yeah, you don't even really technically even have to multiply by pi. So it's just, basically, it's a ratio of the radius squared.
Second squared. Times meter cubed.
And so what do you get, John?
0.14.
0.14
1. That makes sense.
meters
Oh,
per
change
second.
my max. I'm stupid. It's slope. You're not
So notice that that's going,
Also,
this
the
part
question
here is
said
moving really, really slow to make that water out here go really, really fast.
They
Oh,
changed it.
let me see.
They said to use AGH.
Promise you, you better know the difference between isothermic, isovolumetric, and isobaric. If you've never made flashcards, I highly recommend these 3. Okay? Danny,
Baric is the one where the number of moles doesn't change, right?
none of
No.
them in the moles change.
Oh, okay.
None of them have changing moles.
Isomol. They're all.
Baric is same
isomoles.
pressure.
Yeah, baric
Oh,
is
yeah.
the same pressure,
Same pressure, and then you have.
which
the
makes
same
that,
value from all
what
your
does that
other-
look like then on a pressure time graph?
A straight line.
Straight line.
Vertical or horizontal?
Horizontal.
Horizontal. Okay? So if you're going in this direction to the right, if you look at PV equals nRT, what's going to happen to your volume?
It's got to increase.
Yeah, you're gonna make a bigger volume, but you're gonna have the same pressure, so therefore your temperature has to go
Up.
up. So that means I'm going to have a bigger temperature over here. So if you look at delta U
And this is where I get lost every single time.
equaling 3/2 NR delta T, right?
Okay.
So
T's
what's
up,
the value of your delta T?
positive.
Positive. So you can have a positive delta T, which then leads you to a
Positive delta U.
positive delta U. Cool with that.
Mm-hmm.
Nice. Now, what else does delta U equal?
Q plus 3.
Q plus
Work.
W.
Work is done.
0.
Work is 0. You really want to stick with that, gap shot.
Look at the graph.
Oh, no.
Volume changes.
Yeah.
Therefore, there is a force, and it is applied over a
I thought
distance.
pressure was 0.
Work is.
Line.
Positive, I think, and Q is negative.
Now,
I'm pretty sure.
work can equal 2 things. And if you need this specific equation, because it's not on your equation sheet, I'll give it to you. Natural log of VI over VF. And you use that with thermal, because it's a curved line. And then you can have work equals negative P delta V, which is basically nothing more than a fancy way of saying, hey, here's the area of a rectangle, and we're gonna make it negative so that it's consistent, okay? So, in this situation, I don't care about the numbers, just the big idea. So, if the volume is getting bigger, what's the sign of your delta V?
Positive.
You got a positive delta V, right?
Mm-hmm.
True. So then what's the sign of your work?
Negative.
Negative. So,
Q has to be positive.
so Q has to be a positive number, and it has to be greater than
Work.
the work that is done. So that way you end up with a,
Positive delta U. So you have to
Delta U.
put in a large amount of energy.
but only some of it goes to do work. What doesn't go to do work increases the temperature of the system.
So when
That makes sense.
so when volume is expanding,
Work is negative.
work is negative.
Now, let's change it up a little bit.
Push in.
So let's say you're gonna have
Out.
an isothermal expansion, okay? So what's the value of delta U on an isothermal?
Negative.
0. That one's 0. Why?
Because, sure.
No change in
0.
temperature. So then what do you know about Q plus W?
Zero.
They have to be equal and,
Opposite.
so all the energy that's put into an isothermal goes to do work. So it's like, in a little bit, I've got to go over and read to first graders at Craig Woodman. I'm going to give them Skittles, okay? I'm going to dump energy into the system, but I'm going to make them do work. It's like, all right, kids, I'm going to give you Skittles. We're going to go climb up on the roof. We're going to go clean the solar panels, okay? Because, oh man, okay, right? I'm going to make them do work so that their overall temperature remains the same, okay? Now, in this situation, you're going to use work equals nRT, natural log of VI over VF. Why can't I use work equals negative P delta V on an isothermal line?
Because pressure's not constant.
Pressure is constant, and it's not a rectangle, okay? So this is where basically this comes from calculus, finding the area underneath that curve, right? Now, mathematically, which is bigger, your initial volume or your final volume? Final volume is bigger, so therefore you're taking the natural log of a value bigger than or less than 1.
Less than 1. So it's
Less
got to be
than
negative.
1. When you take the natural log of a value less than 1,
Negative number.
work becomes a negative number. Okay, so that way that's consistent whether you use negative P delta V or you use nRT natural log. Okay? With that. Now, Gapshan, what if I do an isovolumetric lowering of the pressure? Now what's my work?
Isovolumetric. 0, 0, 0, 0.
This was your shot, okay? This was your shot, and you're like, I don't, it's 0.
The pressure got to him.
Pressure got to him, literally. So I tried to lower the pressure. So, Gapshan, why is there no work on an isovolumetric?
Delta V 0.
Yeah, there's no change in volume.
There's
There's
no
no
distance.
area underneath the line, okay? So, delta U equals Q plus W. Work is going to be
W.
0.
Not wrong. I mean,
Did you say work was gonna be W?
I mean, yes.
I know you're wearing a Denver Broncos shirt. Okay. Did they win yesterday?
yeah.
Yeah, we did.
Really?
By
Beat
18.
We did.
Indiana?
Whoa.
We made a comeback in the fourth quarter.
Yeah.
You see the
It was
Chiefs let the
wild.
Browns score? That was embarrassing.
Okay, but
What's
hey,
the
at
Browns?
least it wasn't, hey, let's win on a last second field goal.
Yeah.
That's true.
That's true.
Okay.
If that had happened, I don't
If every one score game the Chiefs
So
had
what
went the
makes
opposite direction, they would have 2
isovolumetric
wins.
different than the other two,
worse than the Browns.
other than the
Let them do it
spelling?
and quit.
Well, the W is positive, right?
It's no work.
There's no work. It's 0.
Work is neither positive nor negative. It
I
ceases
feel like
to
0
exist.
is more of a positive number than a negative number.
Did you feel positive about having no money in your bank account?
I know, but I'd feel better if it was
I'm just
negative.
saying, I'd feel pretty negative if my bank account was 0.
Yeah, but I'd feel more
I'm
positive.
just saying, that's me, you know? Okay,
Yes, sir.
notice on isothermal or isobaric, the volume has to change. So you would have to have something where you, with a plunger, that you can move it. What's unique about this one is this is the only one that's a sealed system, okay? So this could be like an aluminum can or some system like your cup, like a Stanley cup or whatever. There can be no change in volume. So what that means is that if you dump energy into the system, all that does is go to change the temperature. None of it goes to do work, okay? So if it's an ISO volumetric lowering of the pressure, am I taking energy out of the system or putting energy into the system?
Energy out,
Why?
because the pressure's going down.
Pressure is going down. So if you have a vertical line and PV equals nRT, the volume is staying constant. So if you're lowering the pressure, what are you going to do? So you got to take Skittles away from the kids. You've got to put it into an ice bath, okay? Let's talk this equation. P equals P naught plus rho GH. So you're here and you're a swimmer. And you swim down below the surface, okay? What's going to happen to the pressure on you?
It's gonna increase.
It's going to increase, okay? So if you have a can with you, what's going to happen, most likely happen to that can?
It will be crushed.
It will be crushed. So what's going to happen to the volume of anything that's pushed below the surface level?
It's gonna
It's going to
decrease.
become smaller if it has that capacity, okay? So like a balloon, something like that, that has that capacity to change that volume, the volume's going to become smaller, okay? Now the opposite happens. If you've ever taken like a bag of, sealed bag of chips in, that you buy like here in Kansas, and you take it like up on the top of the mountain, anybody know what happens to the bag of chips? Yeah, it gets bigger, okay? It gets bigger because there's a lower atmospheric
When I go to
pressure.
Colorado next week, I can, like on Friday, I can test that if you want.
Yeah, take
Yeah.
buy a small bag of like Doritos. Now you have to go, there
Before and
has to be
after
pretty
photos.
You gotta-
substantial
you gotta go way
elevation
up there.
change. So yeah, you can, if you look at the volume here,
You can get
Well, I'm
them.
gonna go ski. I'm gonna go like
Good video.
snowboarding. So.
yeah.
Oh yeah.
Take a
So-
before and after photo.
Now,
Don't
speaking
play.
of skiing,
And
let's talk
If
force
you ever go to
parallel.
Pikes Peak, get the donuts.
How do you calculate force parallel?
I haven't been to Pikes Peak.
Ooh.
Sign.
Sign.
Ooh. Yeah, force parallel sine.
Sign.
Sine times something gravity.
FG sine theta?
Hey, yeah.
Yup,
Sure.
Yup.
Good job.
You
guys.
So-
you got the whole like
I'm really looking forward to a team test.
team test would be
Are
great.
you looking for a team grade?
As in, you split it between all of us, or we all get the same grade?
No, as in I take the number of points that are correct and divide it by the number of people.
Oh.
If you give 600 points of extra credit, I'd be fine with that.
Yeah.
Okay,
Actually,
Do
I
we-
don't know.
so
that was the
here's
final?
Colin going down
Well, I'd be snowboarding.
in my, okay, you're snowboarding. There.
I'm satisfied.
Can we opt out of the final?
Here.
I like to
Dude, you're smoking too. Okay. Snowboarders, dude, don't act like they don't. Okay,
Smoking.
so what are the three forces acting on Colin
Colin
as
was
he snowboards down the hill?
Force gravity.
Gravity.
Gravity, which is gonna act,
Down.
Straight down.
Straight down.
Force normal.
which acts,
Parallel to the slope.
Straight up.
Normal is what holds him from not going down.
parallel is what
wait,
acts
perpendicular.
parallel
Oh, sorry.
to the
Perpendicular.
slope.
Perpendicular. Sorry.
Vocabulary, kids, vocabulary. How do you calculate force normal?
Cosine.
FG cosine.
FG cosine
Theta.
Like we
theta.
just yell out cosine and we just know inherently
Yeah,
that's what we
So, if there is friction, if he's going down the hill, which direction is friction going to act?
opposite the
Up
direction
the-
of motion.
Up the hill, right? How do you calculate force friction?
Force normal over force something. No.
Force normal.
Force
U
friction over
equals,
force normal over force friction.
how about force friction over force normal?
You were closer than I would have been.
Oh,
would have to get
tomorrow's
that.
gonna
Yep,
be
that
a
is right,
long
that is
day.
Krishan, do
What's tomorrow?
Final tomorrow?
I don't. Yeah, I think so.
No, isn't it Wednesday?
It's either Wednesday or.
I think it's Wednesday.
Okay, anyway, get rid of that.
I don't
Now,
know how much I'm gonna
so Colin hits the bottom here, okay, on his snowboard, okay? And let's say there's friction, okay? So, right beside him is the younger version of, and smaller version of Colin. Also on a snowboard. Same snowboards, there's friction. Which one will experience the greater acceleration? Colin or the younger version?
Ooh, wait, whoa.
Wait, so is this after? Have they
No,
gone down
they-
the?
Wait.
you've both hit the bottom at the same time, going the same speed.
The same.
Fours.
And
Oh,
there's the same,
big Colin.
same coefficient of friction between Colin's board and the younger version of Colin.
Same.
Big Colin,
Why?
because he has more force normal.
He
Okay.
also has a bigger mass.
So here's the story.
Hold on, let me look at the equation again.
How are you gonna, on the flat surface, how are you gonna calculate force normal?
FG, essentially. FG, just FG.
How about just mg?
Oh.
Yeah.
Is Colin going to begin to accelerate when he hits the frictional surface on the flat area?
No.
Yeah.
Yes. Yes. Sorry. Yes. Yes.
Decelerate.
He has.
What did you say?
I didn't. Well,
You said the no word.
No, it's a final, so like throw back to. Go back to that.
How
So-
about throw back to me throwing you back? How about me throwing out your final?
You got like take away like 5 points if somebody wrote down their final.
Would that be mass times acceleration?
Yeah.
Yep.
What's gonna happen to Colin's mass?
Accelerate.
Shing.
So what would happen to younger Colin's mass?
Also
Cancel
cancels out.
Uh,
Oh.
Hmm.
Oh, because
Well,
the
the
acceleration
same.
due to gravity is constant.
Wait, so why is force friction mass times acceleration?
Because what's gonna make you slow down when you hit the horizontal part?
Friction.
Anything else? That's your net force, right?
What? So, what's that letter there over there? Is that an M?
What's what letter?
Oh, that's mu.
Mu.
That's totally-
So
That's
if
your
you have the
that's your
same
coefficient
mu,
of friction.
okay, so if mu is the same for both of you, because it's the same, everything's the same.
So we know mu. That's a known. That's a known
Yes.
value.
Now, speaking of mu, what does mu have to be less than?
One.
Or
And it's always a positive or negative number.
Positive.
Positive. If you ever get a negative mu, if you get a negative mu of like -5, that's bad.
Wait, so I
Take a
still-
look at yourself
So,
and make it
if you were to look at a velocity time graph for both of them, what would that look like? Would it be the same?
You have the same slope.
It would have the same slope. Now, let's talk momentum time graph. So let's say Colin has a mass of, make the math easy, 100 kilograms, and Colin the younger has a mass of 50 kilograms. And they're both moving at 10 meters per second when they hit the horizontal portion of the slope. What's their momentum time graphs gonna look like? Well, where's Colin's gonna start at?
higher.
His is gonna, yeah, ironically. He's gonna start at 500 Newton seconds. Colin no, he's gonna start at 1,000. Because it's 100 times 10. Colin the younger is gonna start at
500.
500. Okay, so now they've hit the horizontal portion of the slope, right? This is a momentum time graph. So what's that graph gonna look like?
They're both gonna have the
Parallel
same
to each
weight.
other?
No.
So if that's Colin the younger's, what's Colin the older gonna look like?
Same thing, ending at the same point. Right.
No, same slope. It has the same slope because the acceleration's same. Yeah, and then the area under that is force, right? Maybe. In seconds. Yeah, it's force, right? The area. under
Force?
that
Second
is-
square.
Mass times acceleration.
If you take Newton seconds times seconds to find the area, what are you gonna get?
Newtons.
Newton seconds times seconds.
Oh, Newton seconds squared.
So,
I thought it was a line there.
How does that look like a line? It's a dot. I even said Newton seconds times seconds.
No, over there. It's like that's like half of an N.
Oh, shush.
Okay,
So what's the area underneath a momentum time graph give you?
2 seconds squared.
Which is
Kilogram meters.
nothing.
Nothing.
Oh, okay.
Yeah.
Nothing.
What does the slope of a momentum time graph give you?
Acceleration.
Newtons.
Newtons.
Force,
Yeah.
Or-
It's newtons per second divided by seconds.
Acceleration.
right?
It's good to review.
Just newtons.
Right?
Yes.
Yep.
So if the lines are parallel, what does that mean?
They have the same force.
Okay. Now let's talk about this.
Or the same force is acting on them. Yeah.
If they both start at 10 meters per second and they have the same acceleration,
They're gonna stop at the same point.
Because the same force is acting on them. F equals ma.
hold on.
Wait.
Would you agree that they have the same acceleration?
Mm-hmm.
Mm-hmm.
Yes.
Because that's what we just proved.
Yeah.
So that
Oh,
has
wait.
greater force. Colin has greater force.
Because Colin has a bigger.
Mass.
So, according to your momentum time graph, if the lines are parallel, which one's going to take longer to stop?
Colin.
Big Colin.
Big Colin.
Big Colin.
But you said the velocity time graph stops at the same time.
Mm-hmm.
You have two divergent ideas.
So something is lying.
Just saying, one of us was always right.
Does force friction equal mass times acceleration?
I don't know.
No.
Yes, it does.
Yes.
That's what's making him stop.
Oh yeah.
Does he have a bigger
Oh yeah.
mass?
Because it's yeah. That's the only yes. Sorry. Sorry.
Does Colin have a bigger mass?
Yes.
Yes.
So to stop him in the same time, is that going to require more force?
Yes.
Yes. His line is steeper.
Gershon was right. What do you know?
Yeah, I'm always right, guys.
Oh, it was.
Oh no. Oh no. Look, Mr. Isovolumetric, no. Okay.
0. To be fair, I thought it was gonna end up being a force underneath it. And I thought there was gonna be a greater force. So
Now,
it's okay.
what about a force distance graph?
This I can work with.
Force.
Oh, great. Can't wait to see this one.
We'll see forces in newtons.
Is it
and-
going to be a horizontal line?
Yes. Nope. Yes.
Yep.
Yeah. Mm-hmm.
Force.
Yes.
Because what's the only
yes.
time you have a sloping line on a force distance graph?
You're accelerating.
Force
If
is
you're
changing.
accelerating or if you have a
Spring.
spring.
Yes.
Okay?
Oh, okay.
Which obeys Hooke's law. Okay? All right. So, let's just put in some numbers. Let's just say that acceleration is 2 meters per second squared. Okay? Let's just say. And Colin has a mass of 100 kilograms, so the force acting on him is going to be 200 newtons. True?
True.
Okay? Now, here's the question. Is the stopping distance for both of them going to be the same?
Yes.
Why?
Time.
Because it takes the same amount of time.
What does the area underneath the velocity time graph give you?
The
Displacement.
The displacement.
but
So are they going to have the same displacement?
Yes.
Yes.
Okay. Are they gonna have the same change in momentum?
No.
No.
Which one's gonna have the bigger change in momentum?
Big call.
Big column.
Big column, why?
Because
Greater
he has more
mass and
mass.
velocity
Ah, greater mass,
moving at the same velocity,
moving at the same
and
velocity.
he's got to get to this
So that means
Zero.
more work is done because change in
Momentum.
Because, so the distance is gonna be the same, true,
True.
Uh-huh.
because it's the same area underneath the velocity time graph. So the distance is going to be the same. So is the work gonna be the same?
No.
No.
Who's gonna have more work?
Big column.
Big column.
Why?
Work
More
equals FD,
force.
more force over the same distance.
So this is
More force.
big column, this is
Little column.
Small column.
small column. Okay? Cool with that. So, the area underneath a force distance graph gives you work or change in energy, right? Okay, cool. So that's an interesting way to play that out. Let me see. You have a horizontal table with a block attached here and a block attached there.
Oh, I haven't done one of these in a long time.
The string will fall off the string will fall off the wheel 5 times.
And Colin will screw up the timing.
Okay.
And then Danny's knot is going to come undone and drop the mass.
And the mass on the end of the string
I
will
was
just
back when
magically
we-
fall off of it.
We had like 20% more
And
people
nothing
back
more.
then.
Uh,
Rest in peace to
so
those.
let's say this is acceleration, this is the mass
lost
that's
it
on the
the way.
table.
The mass on the table. works
So, what would this graph look like? So on the y-axis, I'm gonna have the acceleration of the one that has room to fall. Okay? This is the mass that's up on the table. So that goes from 0 up to, let's say this is a 1/2 kilogram mass, and let's say that can go between 0 and 2 kilograms in that gap. So this could be anywhere between 0 and 2 kilograms. So what would the graph look like?
Decrease.
Why?
Wait, what are the things?
Because
Is that
as you increase the mass, you're decreasing the acceleration.
Well, let's start with this idea. What if there's no mass up there? What if that
Then
value
it'll
is
accelerate at
0?
9.8 meters per second squared because that's
it's like
what's
a
accelerating the
Because what's the only force acting on the system?
Gravity.
Gravity. Is that your net force?
Gravity.
no. Yes.
Yeah.
Yes. Sorry.
Yes.
It's the only. Yeah. My brain is.
That's
the
your
only
net
force
force,
acting
right?
on it.
It's the only force.
It's the only
Now
force
remember,
acting on it.
force
So,
net
yeah.
equals force applied plus force opposing. Is this an opposing force?
Yes.
No.
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 No, because there is no
It's
friction
just along
force.
for the ride.
It's just along
It's
to the
just
right.
there.
Does it have mass?
Yes.
Yes.
Does it have inertia?
Yes.
Yes.
Does it resist a change in velocity?
Yes.
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 But it's
Okay.
not.
Oh.
So if
No,
there's
not by
no,
opposing force.
if there's
It's
no
this way.
strings attached,
No friction.
no friction, nothing,
No.
flat, boom, we're just gonna cut the string. What's the net force?
9.8.
Whatever, the 4.9.
Whatever the weight of the
4.9.
object is, right? Which
Yeah.
would be, in this case, 4.9 newtons.
Yep.
4.9 newtons is acting on how much mass?
The half
5.
kilogram.
Half a kilogram. So oddly enough, if I take 4.9 newtons and divide it by half a kilogram, I get
9.8.
9.8 meters per second squared. Wow, how cool is that? Never talked about that before.
Interesting.
Now,
It seems to me that gravity.
what if I make the mass up here a half a kilogram?
Then it becomes 4.9
9
meters per
newtons.
second.
Yeah.
Yeah. Yes.
Yeah.
Because it's the 4.9 newtons acting on 1
If
kilogram.
I put a half a kilogram mass up here, does that have any impact
No.
on that?
No.
No, absolutely not. Why?
It, gravity
force.
does
Just
not
gravity
does
pulling
not
down,
care.
right? And it has room to fall.
Room to
Okay. True?
Give up room to fall.
So, when you get your acceleration on a system like this, what do you always divide by at the end?
9.8? Or no? You get your
To get the acceleration,
mass.
what
mass,
do you always divide by?
Mass of the thing that's being accelerated.
Force equals ma. I don't know.
Yeah,
Over
mass.
Equals 8.
Oh no, the mass of everything.
The
So,
combined mass, you always divide by the combined mass of the system.
Yeah.
Well, everything's being accelerated, so technically I was right.
So, if this is a half a kilogram,
Explode.
the acceleration's gonna be,
4.9.
4.9.
right?
Yeah.
So if you're at 1 kilogram, it's gonna be even smaller, right? So how could we find that?
The same force
We're gonna
over
take 4.9.
divided by the 1.
Now, so if we go to 9.8 to 4.9, then is that gonna be 2.45?
No.
No.
Gap Sean, what's it gonna be? 4.9 divided by
3.27.
3.
27.
Okay? So is this gonna be a linear function?
No. The bottom of McTaggart's lip.
There you go. Now, so is this ever going to reach 0?
No.
Theoretically, no.
No.
So I could put like Saturn up there.
And it would just very, very, very slowly
It
accelerate.
would take quite a while for it to
Okay.
fall.
All right, speaking of Saturn,
Wouldn't Saturn float?
in water.
Probably would
Yeah.
float in air. Most
I don't
things
think
don't
it
float
float in air.
air.
So,
Theoretically, if you could crush Saturn down into a thing that you could just place on the table, hang a mass on the end, and then
Yeah, we can use
The
so
Saturn.
table-
how
the
can
table
you
was meant
use
solid
that
size.
equate
It would-
this?
it
If
would
you
slowly
need
move.
this big equation, I will give it to you.
Oh, the gross one.
I like this equation.
What do you mean you like this equation?
Oh, that's a cool equation.
This equation makes you want to
Stunningly beautiful
explode.
equation.
Ratios.
what equation is this again?
Oh.
What'd you say?
4 pi squared r cubed equals big G mass times t squared.
Planetary motion.
Oh, okay.
You just need to throw out the
So it's
units
been a
before you
while.
start each review. That way we remember, we can like go through our little mental
Radius is
files
in,
back
radius
to
is in meters.
Measured from
The middle.
center
center
mass.
out.
The center
What
of the
units does
object.
period have to be in?
Second.
Seconds.
Seconds.
Because big G is
Second.
Gravitational
Uh,
constant.
And that is
universal
seconds.
gravitational constant, which has a value of
Something.
Point.
It's still on my calculator.
big small number.
6.67
6.7
times 10 to the negative 11.
newtons
So you look at that big small
Per
number.
second.
meters squared over,
Seconds squared.
how about kilograms?
Kilograms.
Something.
Sure.
I'm
I've just been guessing.
I don't know.
Really? That's a shock.
It's on the back of your shoe.
I wouldn't, I'll accept that better that I gave it purposeful thought and still came up with over second squared. Yeah,
There's
that's
no-
disturbing.
There's no help.
There is
Now,
no
on the
purposeful
test
thought.
tomorrow, you're gonna have copies of the yellow sheet and the purple sheet.
Yes.
Okay? You'll have both of them.
Can we have that equation?
Do we get Big Dog?
No.
Aww. Is anyone?
Now, how can you use this to derive Kepler's third law of motion?
You can't. Yeah, you can.
Because the masses don't. You do something and the masses end up canceling out.
So let's say here's a star to be named later, and here's a planet 1,
Very creative name.
planet Danny, and here's planet Preston.
Ooh.
Better?
Planets.
And can Gershon be the star?
So I want to find the ratio of periods and radii for Danny and Preston.
That's just the r cubed over t squared thing, right?
Because if you start with the
Yeah.
4 pi squared
R.
r radius of Danny cubed is going to equal big G mass of the star times the period of Danny squared over 4 pi squared radius of Preston cubed, big G mass of the star over period of
Preston
Preston
cubed squared.
What's
And
gonna happen to the mass of the star?
They cancel.
Cancel.
Those cancel out, miracle of miracles, you get,
R cubed over R cubed equals T
otherwise
squared
known
over
as
T squared.
Kepler's third law. Okay? Now, because if you're doing this, is that have to be in a specific unit?
No, they just have to all be in
No.
the same unit.
Yeah, they just have to be the same because it's a ratio. But if you're doing anything like this where you're actually like, let's say, hey, I'm gonna give you information about Danny, and I want you to find the mass of the star,
Uh-oh.
then what does it have to be in?
MKS.
Then you have to be in the MKS system.
Because
have
you gotta
to
use
be-
G.
Yes, because anytime you're actually using big G in the calculation,
About this.
you have to be in kilograms, meters, and seconds. Now, if I ask you to work a problem like this, what are the odds that I give you all the units in kilograms, meters, and seconds?
Zero.
Absolutely zero, okay? The odds of that happening are absolutely zero. But if this is a multiple choice question and you make that mistake, what are the odds of that answer being there if you don't do the correct conversions?
100.
Very high.
100%.
Very,
Okay.
very high.
Very, very high. I spend more time calculating wrong answers than I do right answers.
And you're a bad person for
I
that.
am. I am a
You're
horrible
so
person.
mean.
I am. I know.
Berg's
every-
like every mistake they could possibly make, and
and
I'll
that
do all
answer,
of them.
it isn't like, oh, the answer should be 5,000 and I give you 0.01 puppies, squirrels, and a cat. No. Okay?
When you're getting answers,
He's like,
completely
I'm gonna give you a
off,
rounding
it's like,
error, and then
choices.
if you did this where you accidentally.
No,
like,
I don't get that nitpicky.
I'm gonna give you a rounding error, and then like I'm gonna use kilometers instead of meters on this one. Okay, boom.
That I will do all day.
Those are your
long.
two options. Oh,
That I would do.
this
all
clown
day
left it
long.
in atmospheres. Kill him.
Sick him.
I'm gonna compress a
Got him.
dart a certain distance.
Newton's grade.
What type of energy am I going to store?
Stream
Us.
potential.
Which is gonna be
1/2 kx squared.
1/2 kx
That's
squared.
my favorite.
K has to be units of
Spring constant. So that's
spring constant, which
whatever.
has units of.
Newtons per meter squared.
Meter squared.
Newtons
Right?
per meter.
Just Newton meter.
Oh,
How
meters per
about
meter.
newtons per meter?
Just meters. Okay.
I think it's a sloping line on a.
It was pretty
Oh
close.
yeah, because it's also the.
It was pretty
Because
close.
if you do Hooke's law and put F here and your elongation here, what's gonna happen? What did you do?
He somehow hit the camera cord.
I did
And
not
then
hit the
kicked the
camera
camera.
cord.
He messed it up.
Quick pan to the ceiling.
Ceiling's
You
still
guys
there,
get
good to hear. It was an earthquake, really.
It was definitely not Cohen.
Definitely was not coming from. So if you graph this, force and elongation,
Where?
the slope of the line is known as
There's spring
the
constant.
spring constant,
Spring.
which has units of
Newtons per meter.
newtons per meter.
And you calculate that one with.
Newtons and meters.
There's no,
There's
it's the slope of a line.
Okay. Yeah.
Rise over run.
Changing Y over changing X.
Sorry.
I'm
Yeah.
just throwing that out.
No, I felt there was the like. Never mind. What, I don't know.
Worse
if you
yet,
know.
let's find the area underneath that.
Integrated.
Integrate it.
Joules.
Yeah.
1/2 base times height, which is going to be Newton meters, which is going to be.
Momentum.
So keep track of this. The slope of that line is newtons per meter. The area underneath is Newton meters.
Yes.
Yes, you could take the integral
You
of.
would get that.
Yes.
So
How
smart.
cool is that?
Interesting.
would.
Can I pan the camera to him to show the smarty pants?
No. We're good. Okay.
Shall remain anonymous.
Because then when I multiply that by meters squared, I get
Newton meters.
Newton meters, otherwise known as joules.
Work.
Okay? Cool. Now, I let go of the spring and it gets launched out. All of that us turns into,
The kata.
how about kinetic energy?
Yeah. Kata.
The kata.
Which is going to be
1/2 mv squared.
1/2 mv squared. Now, if we make that go up a hill,
The kata go to ugh.
Ugh.
Katug.
Us,
I get that.
Us Katug.
okay?
drops in the water.
Let's talk,
It falls then
I'm
on
gonna make
bunch
a
of
wheel
horses.
spin.
It's a Rube Goldberg machine.
What are the things that are going to determine the rate at which that wheel accelerates?
I.
Torque?
Oh, it was actually.
I.
Yeah, but what determines torque?
I finish.
No.
No. Torque is.
Radius.
It does, but that's not what I mean.
Radius is
RF.
FR.
Force and your,
Radius.
Radius.
can you use F equals ma
Nope.
on a spinning
No.
object?
But
No.
you can
No.
use evil F equals M,
The evil.
which is
Oh, E equals m. No. Mainly because where you apply the torque determines
Matters.
your, where you apply the force determines the torque. Now, what else does torque equal?
I fish.
I fish.
Not I butt. Do not I butt.
do not.
Do not I butt.
I butt would be very bad.
I repeat, do
Now,
not I
does
butt.
L equal, that's I alpha. Now,
See?
does L equal,
See, it's an
No,
easy
I
mistake
was-
to make.
no, because you said it, okay? I blame this on you.
Why everything will go in?
Does
L.
L equals?
I
butt.
I butt.
So, why do you spin faster when you bring your arms in?
Your
Because-
radius.
R goes down.
The
Radius
radius.
goes down,
The
your
radius
moment of inertia
Goes
goes
down.
down.
Angular momentum has to be conserved, so butt goes up. Big
Yeah, so
butt.
small eyes have
Big butt.
Big butts.
big butts. Okay. All right. Rotational kinetic energy equals
Rotation.
1/2 I butt squared.
I butt squared.
That's wild.
Does that produce the same
It's
units
just like
as
It ends up as
KT,
joule.
for example?
It ends up as joules.
Because they have to.
Yeah.
yeah.
If they
Otherwise,
didn't,
Yeah.
That'd be a
we go to jail.
bad things would
Some
happen.
energy is
I
just
don't
kind
know
of
that
not
you'd go to jail.
energying.
Now, let's talk moment of inertia. What are the two primary things that determine moment of inertia?
Radius.
Radius and mass.
Radius and,
Mass. I also like shape, because like what shape it is.
well,
Where
which
the
is
mass
how
is
the mass
located.
distributed. What's the only time, what are the two circumstances you can use mr squared?
Thin hoop.
Then hoop and a
Point mass.
point mass. Okay, everything else I would have to give you the equation.
Ooh, are we gonna get like a bug lands on spin ball problem?